Hi, this is Roger from Kanka Labs, and today it's the first part of a new, long-time video series about AM antennas. Now you will ask, what purpose does it make in today's world of web radio and digital radio broadcast? What purpose, what sense does it make to talk about AM antennas and AM reception when apparently the heydays of AM radio are long gone? Well, I think there are many reasons. First of all, AM is not only the medium wave range. There are not only long wave and short wave radio reception. There are also, well, let's say signals in the range from 6 Hertz, which is extremely low frequency, up to the end of the amateur shortwave bands, which is around 30 megahertz. So there is a lot to discover in the AM radio bands. Second is the interest in AM radio is still great, simply because you can learn a bit, and I think it's, for me as a boy, it was really fascinating when I got all the electronics experimental kits for Christmas and for birthday. The king of all experiments, or of all circuits, was always building the radio circuits. It fascinates me until today that even in the best circumstances, you can hear something, you can hear an AM station without any amplifier, without any battery, just with an antenna and a tuning capacitor. If you have the right, and let's call it the best antenna. And there are not only what you probably will know as an AM antenna, this kind of ferrite-rod antenna. There are many types, like this sometimes called spiderweb antenna, or it could be this, which is a loop antenna. There's also the frame antenna, and typical for all AM antennas, they are so-called magnetic antennas, and that has many advantages. We'll talk about that during the series. So it will help you just to find or to build your perfect AM antenna. You can learn about electronics, because we will go step by step from the inductor, which this antenna or this coil is nothing else but an inductor. We'll talk about the resonant frequency and how you tune an antenna to a station. We'll talk about bandwidth and Q factor and figure of merit, and even effects like the skin effect and proximity effect. And there's really a lot to learn, and I'll promise you we will only use one formula per part of this video series and talk very extensively, and I promise you, you will be able to follow this really step by step, and in the end understand a lot about, not only about antennas, but also about electronics in general, because our resonant circuits are everywhere in electronics. They are not only in antennas or oscillators. And so let's just simply start with the first part, where we give a short introduction to what is a resonant circuit, how can you calculate the resonant frequency, how can you tune such a resonant circuit to your station or to your desired frequency. And let's just simply start and see how far we get this time. So if you're new to AM radio, you might think that an antenna always has to look like this way, a simple rod antenna, in this case a very small one. You might know this kind of rod antennas from your FM receiver, and of course you could try to connect such an antenna to your AM receiver, but it's a very bad, if not even one of the worst ideas you can have. The reasons for this are twofold. First is, such a rod antenna picks up mostly the electrical field of your electromagnetic wave, and as you all know, radio waves are electromagnetic wave consisting of an alternating electrical and magnetic field. And well, the electrical field has the disadvantage that in our today's surroundings there are so many sources of interference from nearly every electrical device you have. Take switch mode power supplies or anything else. And all the disturbances are mostly in the AM and shortwave range. So this is one of the best pickups to detect EMI, or electromagnetic interference, and we don't want that. And the second thing is, if you live in houses made of concrete or even of bricks, well, the walls of your house or of your flat, they absorb a great deal of the electrical fields from your electromagnetic waves. So waves from the outside, radio waves from the outside, can be simply absorbed. And well, if we have electrical antennas, then there must also be magnetic antennas, or antennas which are more susceptible to the magnetic field of the radio waves. And you might have seen this kind of antenna, a coil put on a ferrite rod. And this is the most usual type of antenna you could find in radios up to the let's say 60s or 70s. And well, you might say, well, I don't see an antenna. An antenna is this, looking this way, like I only see a coil on a rod, but we later see that this in fact is an antenna. Well, the simple reason is a coil always has to do with magnetics, and we want the magnetic field of the radio wave, of the electromagnetic wave. And you not only can create magnetic fields by sending a current through a coil, the reverse is also true. Every coil will generate a voltage or a current if there is a changing magnetic field, which our electromagnetic waves are. If you send a changing magnetic field through a coil, then of course a voltage is induced. That's the principle of induction. But there's not only this kind of magnetic antennas. It could also take the look of this, which is some windings not over a rod but simply in air, some windings of wire, and you have two ends which go to the antenna input, the AM antenna input of your receiver. But it could also look like this way. This is also an AM antenna. And you can see it's a coil, but it's wound totally different than this one. It's not wound in a solenoid form, but more in a spiral form. And there's good reason for that, and we'll discuss that later. But even this little piece here is a magnetic antenna. If you look closely, you can see there's a coil, and there's even a kind of miniature ferrite-rod in the middle, and by turning it you can tune it. We'll also discuss this later. So magnetic antennas, as we call them, may take several looks and shapes, and if you won't believe it, but even forming a loop out of a piece of coax cable Well, I can't show you the full extent because the field of the camera is too small, but imagine I would form a big loop of one winding with a piece of coax cable. Even this is a magnetic antenna and not the worst one. So there's another reason why magnetic loop antennas are better for AM reception than these electrical rod antennas. Rod antennas have no directional sensitivity, which means when you put them upright, they will receive any signal, any transmitter signal from whatever direction it comes in the same signal strength. So you cannot blank out any station. Well, perhaps a little bit, but the effect is not very great. And that's totally different with these however you want to call them, magnetic coil antennas. You have zero sensitivity in the direction of the rod, which is perpendicular to the coil windings, which means if you have an interfering station near your receiving frequency or even exactly at your receiving frequency, you can blank out the interfering transmitter by placing the antenna rod exactly in the direction where the interfering signal comes from. And with this antenna, which is usually used upright, you can do the same, and you see you have to place the axis of the spiral coil in the direction of the interfering transmitter. And the same is true, of course, with this one. You also have the coil, and the direction perpendicular, the axis of the coil is the direction where you place your magnetic antenna to blank out interfering stations. Well, for that purpose, of course, you have to make your magnetic antenna somewhat movable, or at least turnable. So you have to put it on a miniature turntable or potter's wheel or something like that. Otherwise you would have to turn the whole radio. But perhaps you have already detected this effect as a child when playing around with your AM pocket receiver. So now we've got our magnetic antenna and we have a means of receiving the signal, but we have some other task to do. Imagine that this is your AM band going from somewhere around 500 kilohertz up to 1.6 or 1.7 megahertz. And in this band you have a lot of stations with different signal strength, some very strong, some not so strong. And well, if you only take your magnetic antenna, it will receive all of the stations, and what you hear is either a kind of cacophony of all stations together, or if you are lucky, you will hear the one with the biggest energy, with the biggest field strength, which would be this, and the others are a little bit suppressed. But anyway, what we want to reach is we want to tune our antenna to exactly one station, the one we want. And you know you do this by turning a wheel or pushing some push buttons, but how it is managed, how is it achieved that you can not only receive the signal but tune your receiver to different stations. Well, that's the purpose of combining our coil or magnetic or loop antenna, which is first of all in electrical sense nothing else than an inductor, and I'll use here and as always the European symbol of an inductor. And now what happens if we combine this with a parallel capacitor? You might have seen this circuit already in textbooks, or you may remember it from your physics courses in school. It has many different names, either an LC circuit or a resonant circuit or a tank circuit or a tune circuit. Anyway, it's always a capacitor and an inductivity in parallel. Now, such a resonant LC circuit has two distinct advantages. First of all, the shape of the resonant curve. Well, why is it called a resonant circuit? Because if this is the frequency axis, there is this frequency where the sensitivity is at max, which we call the resonant frequency, and the shape of the curve is somewhat like a bell. And what we want is we want to make it as narrow as possible so that we only receive the station that we want and not neighboring stations, which shall be suppressed because they are here in the lower regions of the sensitivity. So that's one purpose, and we achieve this by making one of the two elements tunable. We could make the inductor here variable, or we could make the capacitor variable, and if we change one of the two values, then the curve shifts from left to right, depending on if you make it bigger or smaller, and that way we can tune our antenna or our LC circuit to different stations. So that's one of the advantages. The second one is, we'll take a look at Wikipedia, because there's a mechanical equivalent to such a resonant circuit, and that looks like this. So here we have the mechanical equivalent of an electrical resonant circuit, and that is the spring pendulum. Now imagine not here the animation. I'm sorry that I cannot show you the English Wikipedia. This animated graphics is only available at the German Wikipedia. Now imagine first of all that the spring pendulum is not moving, it's quiet, and now you're tapping with your finger always at the one frequency, namely the resonant frequency, and always if the mass here is at its lowest point. And what will happen is the amplitude of the oscillation will become bigger with every tap you do if you exactly hit it at the resonant frequency and always when it's at the same position. So any resonator, however electrical or mechanical, is a kind of natural amplifier without any amplifying means. You don't need a transistor or a valve or an op-amp. It amplifies the energy coming in at the exact resonant frequency by itself, and that's quite a nice feature, because that way we not only have a means of tuning our circuit to the desired frequency, but the better the LC circuit is, the more it amplifies the incoming energy, the incoming radio waves, and by how much is determined by what's called the Q factor. Here we see the bell shape of a resonant circuit, and there's this Q factor, which stands for quality factor, or a figure of merit is another way of expressing what Q factor means. And this Q factor determines how narrow our bandwidth is, which means how narrow we can tune or how narrow we can isolate a transmitting frequency, and at the same time it determines the natural, let's call it, amplification of our resonant LC circuit. So it's very important to have a as high as possible Q factor. And how this all interacts we'll see in a minute, and let's go back to the drawing board. Now, before discussing how we can optimize the Q factor, let's go back to our LC resonant circuit and see which ways we have to change the resonant frequency by changing either L or either C. And therefore I've prepared our LCR meter, and we first of all measure the coil which you previously saw over the ferrite rod. And now first of all let's measure the inductivity without the ferrite rod, and we get a value of about 12.3 and something microhenry. And now let's see what happens if we slowly put the coil over the ferrite rod, and you can see that even if I only put it some millimeters over the ferrite rod, the inductivity already has increased by a factor of 2. Now let's move it a little bit more inward, and now we have already 75 microhenry. And let's put it in the middle where you get the maximum inductivity. Now it's 153 microhenry, which is more than a factor of 10 bigger than without the ferrite rod. So by shifting a magnetic material like iron or ferrite over the coil, or putting the coil over a magnetic material, we can change the inductivity and thereby change the frequency. Well, that way of tuning a resonant circuitry is quite rarely employed because it's mechanically quite difficult. You need a kind of lever mechanism to shift the coil, and it's not very linear, so it is a possibility. It's called a variometer. So instead of using a variable inductor, it's much more common to use a variable capacitor, usually in the rotary type. This is one I brought from my collection at home of old variable rotary capacitors. You easily can see how it works. You have two plate packages. One is fixed, which is called the stator, and one is moving and diving with its own plate package into, but not touching, into the static packages. And it's quite precise and quite reproducible and very stable. And it only has two disadvantages. You don't get these types anymore, at least not in new form and in large quantities. And even if, they would be quite expensive to buy. And the second disadvantage is they are quite big. Well, that didn't play a role when radio receivers were the size of a refrigerator. But today everything has to be small, and therefore you don't get them in any large quantities, you don't get them new, and they are quite big. So because of that, in the 1970s, this kind of rotary capacitor was invented. We'll see in a minute that it has nearly the same values of capacitance as this or this larger ones from the old days. But of course it's smaller and it works with the same principle. You can see through this semi-transparent window if there are also metal plate packages inside, but between these metal packages there is some plastic dielectric, like in a film foil capacitor. and this enlarges the capacitance. Here we have air as the separating dielectric material, and air has a dielectric constant of 1, like vacuum. And of course, if we take the plastics that are also used in plastic or film capacitors, then we achieve the same capacity with fewer plates, because the dielectric in between the plates has a higher dielectric constant. Well, that's all theory. Anyway, they are smaller, but they are not as good, they are not as reproducible, but at least you can get them, and they are much cheaper, usually produced in China. This one is our VCAP4, which has all in all, let's just have to count, which has 1, 2, 3, 4, I think 6 plate packages. This one here we'll just measure in a minute, and it has still tuning capacitors here, which are usually not used. And we also use exactly this type, our VCAP4, in our tube experimental kit RT100. And here under this knob is the variable capacitor. I'll show it you in a second. That's the baseboard of the RT100, and that's the backside. And here you can see that we use just the 2 largest plate packs of the VCAP4, of our type of that we decided to take into our shop of variable capacitor. So let's connect our LCR meter with the rotary variable capacitor here on our RT100, and the 2 big plate packages are here at C1 and C2. We'll just measure one of them because they are identical, and it's a bit fiddly. Now we can measure, when it's fully turned to the right, a capacity around 18 picofarad, and if we turn it to the most left position, we get about 290 picofarad. So let's remember that we can vary the capacitance range between 290 and 18 picofarad. Okay, so far for this first measurement, and now let's do some calculations. So let's note what we just found out about our typical AM variable capacitor. It went from 18 to 290 picofarad. And now there's one important formula you need to know, which tells you the resonant frequency of such an LC resonant circuit. I'll promise you it will remain the only formula for this video. And in Germany it's known as Thomson's formula of oscillation, and it says that the resonant frequency is 1 over, just take it a little lower, 1 over 2 pi times the square root of the product of L and C. Now there you can look up this formula every time you want, because every textbook has it, but for this time you only have to remember 2 things. First of all, because L and C are standing in the denominator, that means you get a higher resonant frequency if you lower your value of L or C or both. And of course the opposite is also true. If you increase the value of L and C, you get a lower resonant frequency. Now, what consequence does this have? Just in a moment. The second important thing is that the resonant frequency grows only as with the square root of L or C, or the product of L and C. That means if you quadruple the value of L, you only get half the resonant frequency, and if you quadruple the value of C, also your resonant frequency only changes by a factor of 2. That's quite important, because when we want to vary our resonant frequency, we have to take this into account. We already now can see we have here about a factor of, let's see what it gives. It's 290 divided by 18. This gives us a factor of 16 in the ratio between the highest capacity and the lowest capacity we can reach with our demo variable capacitor. Let's call it 1:16 ratio. So, but this does not translate to a ratio to vary our frequency of also 16:1, but only the square root of 16, and that means that the ratio of the frequency we can reach is only, well, let's call it F ratio, and this is the C ratio. So just remember these two things. The first is because L and C are in the denominator, higher, increasing L or C or both lowers your frequency. And in the opposite way, if you want to get a higher frequency, a greater frequency, you have to use smaller values for L or for C or for both of them. Now, when we take the AM band, we can simply now calculate which inductivity do we need for our demo capacitor, and can we reach the highest and the lowest end of our AM band with a capacitor where you can vary your capacity with a ratio of 1:16, and that's the next thing we'll do. Now, I've just looked up what the limits of the AM band are in Europe and in the US, and let's round it up a little bit. The low end starts at 526.5 kilohertz. Let's take this as 500 kilohertz because we need a little bit of overhead because of tolerances in the L or C. So let's not take the exact value, but a rounded off value. And the higher end is in Europe, it's 1605 kilohertz, and in the US it's even a bit higher, 1220 kilohertz. So let's round this also up to, let's say, 1800 kilohertz. And now let's see if this ratio fits or is reachable with our demo capacitor, which has a capacitance ratio of 16:1 and a frequency ratio of 4:1. Now 1800 divided by 500 is a factor of, thank God, it's only 1 to 3.6 F ratio for the AM band. even if we are quite generous about the limits. So you need at least a capacitance range or ratio of 1 to 3, better 1 to 3.6, and if you have, as with this capacitor, a 1 to 4 ratio, you safely will reach both ends of your AM band, and you still have a little bit of overhead for tuning to somewhat for tolerances in your inductivity or in the rest of your circuitry, and for doing some experiments if you even find stations which are outside the official AM spectrum. Now, I promised you only one formula in this video, but we can play around a little bit with this formula, because we now want to calculate the value of L, and even if you have forgotten your high school math, it's quite simple. It's 1 over 2 pi times the resonant frequency squared times the capacitance C. And by the way, if you want to calculate C, you just can swap L and C. They are interchangeable. And now let's take an example with our circuit. We know, remember, the highest capacitance is responsible for the lowest frequency, and the lowest capacitance is responsible for the highest frequency in our resonant circuitry, because L and C are in the denominator. And now let's just calculate which inductance do we need here to tune our circuit with this demo capacitor to the AM band, and we can choose either the lower or the higher value. Let's, for some special reason, take the higher value, and this gives us 2 by pi times the resonant frequency which belongs to the highest capacitance value, which is in our case, for safety reasons, 500 kilohertz. This gives this value. Now we have to square it, and we have to multiply it with our capacitance here, which belongs to the where we want to reach the 500 kilohertz, and that's the high frequency, 200. That's the high capacitance range, 290 picofarad. And now we still have to take the reverse, because first of all I only calculated the denominator. Let's search for the reverse, and we get a value of rounded, it's 350 microhenry in our example. Now let's check with our LCR meter if the antenna coils that we already saw in the beginning do have the right inductivity for AM reception with our demo variable rotary capacitor. We connect the litz-wire, and it's as always a little bit fiddly and takes a few seconds, and then the LCR meter still has to get the right value, and we get only 150 microhenries. So what did they do at Kainka Labs? Did they wind the wrong coil? Well, let's compare it to the one I have wound by myself, and we don't have to check it. It's already written what it's nearly the same as the ferrite-rod antenna. It's only 170 microhenries. You say there's something wrong. Now the reason is simply that these antennas are intended not for a 290 picofarad capacitor, but for a 600 picofarad capacitor. And you may remember on our Pt.1 board we have two plate packages which we can put in parallel, and then we get this the necessary 600 picofarad. And the same, I wound this coil for this kind of rotary capacitor, and it also has around 600 picofarad. And that's the reason why these AM antenna coils have a somewhat lower inductivity than what's calculated for a 290 picofarad. Now, if you recalculate it, you will still get quite a difference. That's why we made some generous assumptions about our frequency range. In fact, due to some tolerances, it only has to start at 525 kilohertz, and we still can add some little extra capacitance if we don't reach the lower end of the AM band. So in fact they are exactly made for the lower end of the AM band in connection with either two packages of this one in parallel, or a variable capacitor which has from the beginning with one big plate package 600 picofarads, and that's everything has a meaning here. So now let's still measure the other two coils we had, namely this one, which is from a commercial FM AM hi-fi stereo receiver. And now we get a little surprise. This one seems totally out of range with only 18 microhenries. It's a factor of 10 away of what we would expect. Now this antenna is apparently not directly suitable for AM receptions. There must be either a trick inside the receiver or some other means how to use this as an AM antenna, but you cannot use this one directly with an LC-resonant circuit. And we still had a fourth, this miniature coil. I have to search the wrong windings. And what does it give? It gives 100 microhenry. Well, that is at least suitable for the not for the low end of the AM band. This little coil originally was not intended as an AM reception coil. It had some other purposes, but with the right capacitance setting, it can at least be engaged for a great part of the AM spectrum. So it's quite of a compromise, or a dual use coil, originally intended for a metal detector kit, but also usable as a miniature AM receptor coil, AM antenna, at least for part of the spectrum. So now we want to see if we can really see in reality when we connect one of our AM coils with a rotary variable capacitor, if we can find some way of seeing either on an oscilloscope or whatever the resonant frequency. And that's part of the next experiment. So now let's see if reality meets theory. As you can see, I have connected the two packages of our variable capacitor in parallel, and put some wires and some clamps, and I take the big coil, the spiral coil, connect the two clips. Just a little difficulty in front of the camera. And now I'll show you an ingenious measurement device. It's called a dip meter. This one is the most advanced or most sophisticated one I saw. I won't explain in detail what a dip meter does and how it works. I will give you the link below in the comments where you can get this and where you can get information about this. Anyway, you see we have no voltage source here. We only have the capacitor and the coil to form a resonant circuit. And I've put the capacitor on the low end range, which means highest capacity. And our task is, will this coil and the two parallel packages of the capacitor reach the low end of the AM spectrum? And therefore, I'll try to make it that you can see it. I'll tune here's the frequency. The point in the middle is the kilohertz indicator. And I'll try to tune it upward until this red LED starts to light, which is now. And this is and you see we have really no battery. This coil here puts some radio frequency energy into our resonant circuit, and it is kind of reflected back into the secondary coil. And by scanning a little bit around the frequency, it searches automatically for the maximum and displays it as a frequency. So the maximum here is around 485 kilohertz. So that's the lower end of the combination of this antenna coil with 170 microhenry and the maximum setting of our paralleled plate packages of our capacitor. So that is definitely what we want it to be, somewhat below the lower end of the AM band. And now let's check the high band. For that reason I have to change this coil. As you can perhaps see, this one is for the range 350 to 750 kilohertz. Now I put the right coil for the high end of the AM band, and we turn it not completely to the right, and let's try to search until the red LED goes on. There we are. It's also sometimes a bit difficult to find the exact frequency, but we are around 1.6 megahertz or 1600 kilohertz, and we are not completely at the right end. Now let's turn it fully up and see if we can find again the resonant point. No, not quite. I put it to the maximum of 1.6 megahertz, and yeah, there we are. So even if we are not quite at the end, we reach around 1.6 megahertz, and we still have a little left. The reason is with this coil I can only go up to 1.6 megahertz or 1600 kilohertz, as you can read, from 800 kilohertz to 1600. That was the reason why we couldn't exactly reach the endpoint, but we can be quite sure that we can reach at least 1.7 megahertz or 1700 kilohertz, and this is the upper end of the AM band, even in the United States. In the rest of the world it's usually 1.6 megahertz. That's why I want this coil only for this range, and well, that way we can be sure our calculations are right. the coils that we wound or that we sell are right, and theory really has met reality. And so that was, I think, quite interesting. If you want to know more about this dip meter, I already told you it's not by Kanka Labs, not by Akamadulbus. It's a kit invented, or a circuit and a kit invented by German Ham radio amateur, and I will give you the link where you can get this as a kit. So that was it for the first part. You probably noticed that I was speaking a lot slower than usual. That has two reasons. The first is I recorded this even nearly 1 year ago and didn't find the time to finish it. The second reason is simply that you can better follow the topics. And so next time we'll talk about more in detail about the Q factor, the bandwidth, the damping factor, how they all are hanging together, and what you can do to get really the best Q factor, the best figure of merit as it's also called, out of your resonant circuit. So that was it for today. I hope you liked it. Thanks for watching. Until next time. Bye from Roger. Bye from Kanka Labs.